So this is a video where I'm going to go over section 18.6 from our coverage of chapter 18. And I'm going to start with here just a discussion of how we think of acid strength relative to nonmetal hydrides. Then we'll talk about oxoacids and then hydrated metals as well. So first, in this slide, I just want to go over the concept of what is a nonmetal hydride. So here, E is our nonmetal element, and our hydride is just going to then be the nonmetal element with hydrogen. And so here we have two points that affect the acid strength of a nonmetal hydride. And first of those is the electronegativity of the nonmetal, E. And of course, we know as you go across the period, the electronegativity increases. So fluorine has the highest electronegativity, oxygen is next, and it goes down. And so what we find is that acid strength of FH is greater than acid strength of H2O, which would be the oxygen hydride. Now another factor that is in play here is the strength of the EH bond also affects acid strength. And so given these two factors, what we in general see is that across a period, the acid strength will increase. And so electronegativity increases that way, and so the acidity of the nonmetal hydride increases across the period. Also, down a group, the acid strength will increase, because going down the group, the length of the EH bond will increase to the point that the bond strength decreases. So we have to be careful on this one, because you say, well, electronegativity increases as you go up a group, and down a group, electronegativity is going to decrease. So you might look at this one and you might think, oh, going down a group, the acid strength should decrease. But remember, when we talk about going across the period, it's mainly going to be electronegativity. When we go up and down a group, it's mainly going to be about bond strength, the EH bond strength. So here, basically, as E gets bigger, the bond gets longer, and the strength, therefore, decreases. And that's really the rationale. As you get a bigger and bigger element, the bonds get weaker and weaker as they get longer, and therefore those protons come off more readily, making it a stronger acid. And so this is kind of illustrated in this slide, where we have electronegativity causing the acidity to increase going in this direction. But when we have elements that are, these are elements that are of similar size. However, when we have elements changing in size, and so the bond, the H to element bond length gets longer, then we have acidity increasing this way because of bond strength decreasing. So HI is a stronger acid than HCl because of the size of I. I is quite a bit larger, and the HI bond is therefore longer than the HCl bond. And so HI is a stronger acid. Now, we also see here that as we go down, we get acid strength increasing as well for the next group over. So for H2O is the weakest acid, but H2S is a stronger acid, and so forth. You see acid strength increasing as you go down. Now the next topic then is oxoacids. Oxoacids are basically going to be a central atom with oxygens bound to them, so they're going to be polyatomic anions. And so these polyatomic anions that have hydrogens associated with them, we have a group of them, and we'll talk about why this is so, but or how the acid strength varies for them. But all oxoacids have the acidic H bonded to an oxygen atom. Okay, so if you have a say something like sulfuric acid, where you have sulfate with two hydrogens associated with it. Those hydrogens are going to be bonded to the oxygens of that sulfate. So sulfate would be an example of an oxoacid. Nitric acid would be an example of a oxoacid, and so forth. So acid strength of the oxoacids depends on electronegativity of the central element, nonmetal element, E, and the number of oxygens that are surrounding the E. Now, oxoacids that have the same number of oxygens but have a greater electronegativity of E, the acid strength will be greater. So if the number of oxygens are the same, but the only thing different is the electronegativity of E, then the greater electronegativity, the stronger the oxoacid for this instance. Now, if you have different numbers of oxygen atoms, then acid strength increases with different numbers of oxygen atoms. And so these are basically the two kind of rules associated with oxoacid strength. Now, the relative strength of oxoacids then would be illustrated here, that as we have greater electronegativity of the E, so this would be our E component here, and as the electronegativity of the E, the nonmetal atom, is greater, then we have more electrons pulled away by that. And so the greater electronegativity of this guy pulls more electrons away, thereby making this less partially negative. Okay, so this guy right here is in essence what's holding on to the hydrogen, but if you pull electrons away from this, you reduce the magnitude of this partial negativity, and that makes the hydrogen easier to come off. Now, a similar thing is going on when we have an oxoacid like this, that not only are we pulling electrons away from here, but by this atom, but we're increasing the pull by adding oxygens out here. So oxygen is fairly electronegative, but if we pull the electrons away from it, then that reduces that and decreases the size of this guy right here. We decrease the size of that, we make that a better acid. And so basically acid strength means this comes off more easily. That's a stronger acid. The next one that I wanted to talk about is hydrated metal ions. And so with a hydrated metal ion, these are going to be things that have metal ions that have water associated with them. So water molecules will be associated with metal ions in solution, and these hydrated metal ions can form acidic solutions. And so if we have a metal ion that associates with water, then what we have is a metal hydrate complex here in solution. Now, if the metal is small and highly charged, then it will withdraw enough electrons away from the oxygen-hydrogen bonds to release the hydrogens more readily. So in essence, what this metal does is it increases the acidity of water-bound protons. So water-bound protons are not highly acidic, but if we have the water associate with a metal like we do here, then we can increase the acidity of these protons. And that's in essence what we have going on. Now, the way this would be our metal hydride, our hydrated metal here, will react with water to give us basically a hydronium ion, and we would then have our metal complex minus a hydrogen, and we would have the metal complex would then be basically down by a hydrogen. So instead of we would have one less water molecule, right? So X minus 1, and then we would have a hydroxide ion associated with the complex now. So how does this look? Well, let's just take a quick look at a picture of it. So aluminum, hydrated aluminum, has acidic behavior, so hydrated aluminum ion. And basically, the hydrated aluminum ion in solution is believed to look somewhat like this, where the water molecules here are surrounding the aluminum. This then pulls the electrons away from these oxygens that are interacting with the central aluminum, and that makes the OH bond more susceptible to loss of a proton. And so we have a nearby water molecule can come in and can pull off one of these protons here. And so that's what we wind up with a hydroxide and our hydronium ion here.